Welcome to Winning Edge. Today we'll discuss about hydrocarbons. All fuels we use in our day-to-day lives are nothing but hydrocarbon compounds. Petrol, diesel, and paraffin wax, everything we will obtain are obtained from crude oil. Mining of these hydrocarbons is one among the greatest business in today's world. We having different usage of these hydrocarbons in our day-to-day life. Like we are using many deodorants, sprays that usage these hydrocarbons. You will be surprised to know that many hydrocarbons that will exist in gaseous state on Earth will do exist on different solar planets and their satellites as liquid. Like we have ocean of water on Earth, there is ocean of methane on Titan. Hydrocarbons can be broadly classified into, depending upon what type of carbon-carbon bonds are present. Like we can have alkanes, which are having double bonds, and alkynes having triple bond. These hydrocarbons can be further classified as saturated hydrocarbons that contain only single bond between carbon atoms, or they are described by general formula CnH2n plus 2, where N is the number of carbon atoms and H2n plus 2 is number of hydrogen atom. For example, for methane, C1H21 plus 2 is nothing but CH4, simplest hydrocarbon. Another class is unsaturated hydrocarbons, having multiple carbon-carbon bonds, like it can be double bond, triple bond, or both of these bonds can present in unsaturated hydrocarbon molecule. Sigma bonds are single bonds and pi bonds are present in case carbon-carbon double bond or carbon-carbon triple bond is present. Like in triple bond, we having 2 pi bonds and 1 sigma bond. Next class is aromatic hydrocarbons. Aromaticity of a compound is decided for all the ring systems. Whether the ring system is benzene based or not a benzene based system, it is aromatic or not is decided by few characteristics as first criteria is planarity, whether all the carbon atoms lie in a single plane or not. Like this structure, all rings are present in a single plane. In benzene, all carbon atoms present in a single plane. Similarly, toluene, all ring carbon atoms are in a single plane. Phenol and aniline follow the same characteristics. Next criteria is complete delocalization of pi-electrons and ring. It It means all electrons should be able to delocalize over a ring. It is possible only when we have alternative carbon-carbon double bond or carbon-carbon triple bonds. Next is presence of 4n plus 2 pi-electrons in the ring where n is integer starting from 1. So total 6 pi-electrons are present in benzene ring, so it's aromatic. And this aniline structure, we are having a total 42 pi-electrons, which satisfies 4n plus 2 rule. So rules for aromaticity are: first is planarity of a molecule, next delocalization of electrons over the whole ring, third is presence of 4n plus 2 pi electrons. These rules are consolidatively called Huckel Rule, starting with the alkenes now. Synthesis of alkenes. First, hydrogenation of unsaturated hydrocarbons. In the synthesis of these saturated hydrocarbons, which are nothing but alkenes, we may have a starting material unsaturated hydrocarbons, and we'll add hydrogen atom to these pi bonds to make saturated hydrocarbon. This reaction will happen in presence of catalysts like platinum, palladium, and nickel in their finely divided state. This is a finely surface of these element atoms when we finally divide these metals into the fine particles. Hydrogen is absorbed on the surface, and this surface activates this hydrogen molecule at individual atoms. Before, there is an important point to remember. In case you use platinum or palladium as a catalyst, reaction will happen at room temperature. Or in case nickel is used as a catalyst, in such cases higher temperature and pressures will be required. So absorbed hydrogen dissociates into individual atom, which is nothing but activation of atoms, and these atoms interacts with the pi electrons of alkene here, and finally what happens, finally divided these elements, nickel, palladium or platinum, will provide greater surface area and greater absorption, and we are getting saturated hydrocarbon. Hydrogen atom attached to these double bonded carbon atoms to make saturated hydrocarbon. Next reaction is synthesis of alkenes from alkyl halides. Alkyl halide on reduction with zinc and dilute hydrochloric acids give alkene. In this reaction, one of the hydrogen atoms splits to make hydrogen chloride. Other hydrogen atom attaches the alkyl group to give hydrocarbon. This reaction is possible only for HCl, HBr or HI, means where this compounds is either methyl chloride, methyl bromide or methyl iodide. This reaction is not true for methyl fluoride. Zinc offers again as a activation surface, Next reaction is Wurtz reaction. In this reaction, alkyl halides on treatment with sodium in dry ether gives higher molecular weight alkenes, mean the number of atoms, carbon atoms in a chain will increase in the Wurtz reaction. This is what the Wurtz reaction is. Having a methyl bromide and sodium metal in dry solvent, what we are getting is ethane and sodium bromide. The reaction will be first our alkyl bromide splits to give us bromide free radical and alkyl free radical. You see here. So first we will see a reaction between sodium alkyl radical and free radical of alkyl group and sodium metal atom. We know sodium got very low ionization energy, so it easily transfers this electron to alkyl radical to make alkylide carbanion. That's what happens. And this carbanion formed act as a nucleophile to attack another alkyl halide to give us new alkyl group and sodium halide. So you see the chain length has been doubled in this Wurtz reaction. And the another sodium anion that has been used earlier, let us say sodium halide. So for each mole of alkyl halide, 1 mole of sodium will be consumed in this reaction. Another reaction is decarboxylation of carboxylic acids. Sodium salts of carboxylic acids on heating with soda lime, which is nothing but a mixture of sodium hydroxide and calcium oxide, will provide us alkane. But alkanes have 1 carbon atom less than carboxylic acid. You see here, this is nothing but sodium acetate. You heat it with sodium hydroxide and calcium oxide. We getting out product is methane. You see from here, CO2 goes out, and this will form sodium carbonate. Another decarboxylation reaction is called Kolbe electrolytic method, also called Kolbe's decarboxylation method. In this reaction, we are using electrolytic cell and solution of sodium acetate. It can be anything else as well, but here we are taking an example of sodium acetate. We are having an anode positively charged and cathode negatively charged. On passing current, what we will see, negative part of the solution, that is the acetate ions, start moving toward anode. What happens that anodic surface? Anode strip off the electrons from anode, from acetate ions, and what we left with is this acetyl. This acetyl free left with this leads to this acetate free radicals which undergo homolytic cleavage give us methyl free radical. CO2 escapes from our anode. Methyl free radicals are fairly reactive. Now these reactive radicals will combine with each other to give us ethane, which is gas again escapes, can be collected from anode. Now, so far we have talked about synthesis methods